Have you ever wondered why we learn factoring? Well, one of the important reasons that we learn factoring is because it's very useful in helping us solve equations and inequalities. I'm going to start by illustrating with the following quadratic polynomial, negative 3x squared minus x plus 10. Let's start by factoring it. A strategy that I like to use is to multiply the terms to get negative 30. And then I think about what factors of negative 30 will add to negative 1. At some point I should realize that negative 5 times 6 or 5 times negative 6 is going to work. And in this case I want to look at 5 times negative 6. So I'll split this. Negative 3x squared minus 6x plus 5x plus 10. Notice that the two terms with the x combine to give me my negative x. Now I can do grouping. Factor out negative 3x times x plus 2. Factor out a 5. So I get 5 times x plus 2. And now I look and I see that I have a common factor. That's the method of grouping. So I factor it out. And I get my factored version, negative 3x plus 5 times x plus 2. Now the reason the factoring is useful for equations is that if I have a number a times a number b, the only way that can equal 0 is if either a is 0, the first number, or b is 0. So if I go back and I look at my original function, my polynomial, and I say, when does that polynomial equal 0? I've rewritten it in a product form. And the only way that this original quadratic can equal 0 is if the first factor, my a, is 0, or my second factor, my b, is 0. So suppose I was given the equation, when does negative 3x squared minus x plus 10 equal 0? Well, I've factored it. Let's get the right factor in there. I factored it. And so if I rewrite my equation instead of the addition formula as a product formula, the only way that this can equal 0 is if the first number equals 0, and the first number was negative 3x plus 5, or the second number is 0, and the second number was x plus 2. Now the advantage of this is my original formula was a quadratic. My new formulas are both linear, and so I can just solve for x by isolation. So in the first case, the first number would equal 0 if x equals 5/3, and the second number would equal 0 if x equals negative 2. So I get two solutions. Either x equals 5/3 or x equals negative 2, which gives me my solution set to my equation. The numbers negative 2 and 5/3. Suppose instead of solving an equation, I was asked to solve an inequality. Same polynomial, negative 3x squared minus x plus 10 is greater than 0. Well, again, let's use factoring. Now at this point, a lot of students actually make a mistake. For equations, we said the first number is equals 0 or the second number equals 0. And a lot of students want to do the same thing with inequalities. They want to say the first number is positive and the second number is positive. But that's not the only way to multiply two numbers to get 0. I could have multiplied two negatives. And so what I want to do is I want to use parity rules. Parity has to do with even and odd. If I have an even number of factors, for example, negative 2 times negative 3, the negatives cancel, and I'm left with a positive number. But if I have an odd number of negative factors, like negative 1 times 4, well, the answer is negative. So the key is not that both of them are greater than 0, but I want to know how many of the factors are positive and negative. One of the fastest ways to do that is to create a number line and to mark down all of the points that we found for the equation. In other words, where it equals 0. Let's see, if I can remember, this first factor was 0 at x equals 5/3. That was where it's equal 0. The second factor was equal to 0 at -2. Now, what I can do is I can pick numbers in each of the intervals and then decide if the first factor was positive or negative, and if the second factor is positive or negative. So for example, in this first interval, I might pick the number -3. If I plug -3 in, I get 9 plus 5. I don't need to know the number, I just need to know the sign. The first factor was positive. Then I put -3 in the second factor, and I get -3 plus 2, I get -1. All I need to keep track of is the sign. I'm counting how many negatives. There's one negative factor. And so my answer will be negative by parity. If I pick a number between -2 and 5/3, for example 0, I plug 0 into first factor, I get positive 5. That's a positive number. And I plug 0 in the second factor, I get positive 2. That's another positive factor. And this time I have 0 negative factors. That's an even number, and so my product is positive. Now 5/3 is 1 2/3, so if I pick the number 2, I'll be on the other side of the point. If I plug 2 in, I get -6 plus 5, that's negative. And if I plug 2 in here, I get positive. Again, I have one negative factor, that's an odd number, and so my parity rules tell me I have a negative overall sign. Notice I'm not actually solving individual inequalities, although in a sense, checking the signs of the factors is actually doing that. But what I'm doing is I'm checking parity rules based on my factors to determine the signs on each interval. My original inequality that I was asked for was asking, when is my product a greater than... The question that it was asking is, when is that product greater than 0? Which means positive numbers. Corresponds to this middle interval. And so the solution to my inequality is the interval from -2 to 5/3. And so factoring can be used to both solve an equation as well as an inequality. When dealing with inequalities involving rational functions, which are fractions involving polynomials, I have a function is less than or equal to 1. I can't use factoring in this current form. And the reason is factoring is only useful to use the parity rules, which means I need to be comparing for positive and negative numbers, not bigger than or less than 1. In order to solve this problem, I need to transform it to a problem that can be answered in terms of being positive or negative. And I do that by moving everything to one side. So now I have a question involving positive and negatives. I have a function on the left. I want to know when it's negative, less than 0, or equal to 0. Now, it's not factored. And the reason it's not factored right now is because the last operation is subtraction. What I need to do is I need to combine those terms into one fraction that I can then factor. So I'll do that by finding a common denominator. Common denominator is x squared minus 9. So I need to multiply this term by x squared minus 9 over x squared minus 9. Then I can add. All right, with a little hesitation there on that last term, we find that the formula can be rewritten as negative x squared minus 3x plus 10 all over x squared minus 9. So my question has now been transformed into the following. We want to know when this function is less than or equal to 0. Now it's almost factored, it's in a quotient. What I need to do is I need to factor the numerator and the denominator separately. First, I'll factor out this negative sign. I always factor out my negative sign. What that does is it changes the sign of every term inside. X squared minus 9 is a perfect difference of squares. So I get that that's x plus 3 times x minus 3. And now let's factor this quadratic that's left. Notice it's x plus 5 and x minus 2 to give me the value 3 in the middle. So by factoring, I can replace that original formula with the factored form. My formula has 5 factors. The negative sign, which is negative 1, the factor x plus 5, the factor x minus 2, and then 2 division factors, the factor of 1 over x plus 3 and the factor of 1 over x minus 3. I don't necessarily need to write all this next part down, but what I want to do is I want to pay attention. When do each of the factors change sign? First factor, negative 1, never changes sign. The factor x plus 5 changes sign when x plus 5 equals 0, which is at x equals negative 5. The factor x minus 2 changes sign at x equals 2. Now, to divide by x plus 3, it's never actually equal to 0 because 1 over something can never equal 0. But it changes sign at x equals negative 3. And if I plug negative 3 into my formula, the formula is not defined. So this is an undefined point. Similarly, the factor that comes from dividing by x minus 3 gives us a second undefined point. I usually do all of this in my head, and then I summarize it on a number line. A factor changes at negative 5, at 2, at negative 3, and at 3. And negative 5 and 2 are both places where my formula equals 0 because I multiply by a number that's 0. The numbers 3 and negative 3 are undefined points. Because I can't divide by 0. Now, in a similar way to our last example, we now want to decide what sign each of these intervals have. So I have 5 factors. The first factor is always negative for the negative 1. Now let's pick a number like 4, and that'll be positive, and that'll be positive. And if I plug 4 into the denominator terms, I get positive and positive. I have one negative factor. That's odd. Parity rules tell me the answer is negative. Now, between 2 and 3, the only factor that changes is the x minus 3 factor. So for example, if I plug in 2.5, I get negative, positive, 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 negative. So I get negative, positive, 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 negative. Now I have 2 negative terms for an overall sign that is positive. And I'm going to have a pattern like this. Each time I cross one of these factor points, that corresponding factor changes sign. That happens to be because each of the factors appears with multiplicity 1. In certain problems, if it's ever even power, for example, if this was squared, when it changed sign from positive to negative, it'd be positive squared and negative squared. It wouldn't actually change sign. In our case, each of them has power 1, and so they'll change sign each time. I can anticipate the final answers: negative, positive, negative, positive, negative. Just to clarify one more example, here in the middle between -5 and -3, I might pick -4. So I get negative 4 plus 5 is positive, -4 minus 2 is negative, over negative and negative. I have a total of 4 negative numbers multiplied together. That's an even number of negatives. Parity rules say it's positive. Okay. We've done sign analysis. We have a number line that summarizes everywhere. It's negative, positive, and I can now answer the question. I was wondering, when is this formula less than or equal to 0? Which means, when is it negative? We have 3 intervals. And when is it 0? I have 2 points. These other 2 points are undefined, and they're not equal to 0 there. If I were to draw a graph of my number lines, I'd be the interval up to and including -5, from -3 to 2, and from 3 on, not including 3. And this interval is -infinity to -5, including -5, -3 to 2, including 2, that describes the middle interval, and 3 to infinity. So factoring is useful because it helps us solve equations and inequalities. It does that because the factors equaling 0 cause the product to be 0, and the number of signs that are negative allows us to determine whether the overall product is negative or positive. All right, good luck.